So, here we go. So let me just remind you that in the first lecture we learned about life. In the second lecture we learned about the elements that were implanted in the Earth one way or another to create the molecules that are required for life. And then we saw some kind of widgery, right? Going and get soil from other planets or other asteroids, bringing it back. Then we heard from our biologist, and we heard how you can actually go from simple molecules to create the diversity and the scaling that we know that the Earth has. Now, I'll remind you all that nobody's been able to figure out how to make a cell, but other than that, we're doing okay. And the other important thing we all learned is that you have enough heartbeats for 50 years. So clearly that scientist is unencumbered by the facts. And then we heard last time about how you can make very complex entities from very simple entities, right? Complexity. Today we now go back, and what we've learned from our biologists and we think we understand from simple chemistry and complex biochemistry, today we go and look for life in our solar system. And boy, can we do that. Planetary Sciences, the Lunar and Planetary Lab, and Tim Swindle, who you'll hear about today, is the director of that lab, has an amazing history. It was created to map the moon so that the Apollo mission would actually hopefully land safely, which they did. It's been involved in more planetary exploration than any other university in the country, and in fact, if you add all of our competitors together, and these are the Caltechs and the Cornells and the MITs, the kind of research funding that they get, and you add it all together, it's less than what our Lunar Planetary Lab gets. That gives you a sense of what is going on. So today we have the director of the Lunar and Planetary Lab, which in itself is an amazing distinction, Tim Swindle. And Tim is going to tell us about what we know about exploration in the solar system. Tim got a PhD in, got a bachelor's in journalism, physics, and mathematics from Washington University. He came here and has been here with us really since the beginning of his career. He does something really interesting. He looks at noble gases in asteroids, and it's by looking at these noble gases that you can figure out if they actually came from Mars or some other planet where we think we understand what their atmospheric composition is like. Tim is an amazing teacher, and one of the interesting things that he does for a living is he goes to Antarctica to collect asteroids and so on. It's easy to find him there because they're sitting on top of the snow. That's why they do it. And he has fame because he also has an asteroid that's been named after him. So there's a Swindle asteroid. Has a piece of rock. How many of you have a piece of rock named after you? Tim, welcome Tim Swindle.
Did you want to talk about the acknowledgments and stuff, or
sorry?
The acknowledgments? Or? Okay. Thank you, Joaquin. I grabbed the wrong one. I can run a lab, but I can't find the right remote. My wife could tell you that. So, we've been hearing about what life is, or how much we know or don't know about what life is. We've heard about how it might get started. But a lot of these questions, what we really want to know to understand what's going on, we'd really like to know about life version 2.0. We'd like to know about life somewhere else in the solar system, some life that's independent of the life on Earth. And so what I want to do tonight is to talk a little bit about the searches we have made in the solar system for some other form of life, life 2.0. So if you're out camping, and you're lying in your tent and you hear some noise outside, the logical question to ask is anyone out there? But then, if you step out of the tent and you look up at the sky and you see all those stars and the planets and the moon, the same question holds. Is anyone out there? And if you're a scientist, you start thinking, well, how could I figure out if anybody's out there? the idea that there could be life elsewhere in the solar system really gets its start with the Copernican revolution. Copernicus had this revolutionary idea that the Earth is going around the sun rather than the other way around. And others quickly realized that if the Earth is just a planet going around the sun, maybe the other planets are worlds like the Earth. And this gentleman, Christian Huygens, we'll hear a little bit more about some of his discoveries later, he said that, well, if the Earth's just a planet and there are these other planets, it's not improbable, there's the scientist speaking, that the rest of the planets have their inhabitants too, as well as this Earth of ours. So where would we look? The obvious place to start, of course, is the Moon. It's our closest neighbor. Even with the telescopes of the 1600s, you can see features on the Moon. You can study it. But the problem is, if you're looking for life, those features don't change. They're the same day after day, year after year. There's no atmosphere. You never see any clouds disturbing those features. And so, by the early 1800s, scientists had come to the conclusion that there's not life on the Moon. Until, in 1835, a daily newspaper in New York called the New York Sun came out with this series of increasingly spectacular articles about this noted astronomer who had turned his telescope backwards so that it worked as a microscope looking at the Moon. And every day there were progressively more outrageous discoveries, culminating with these characters, these winged characters flying around on the Moon. Well, it's not clear whether it was just a hoax to drive up circulation. It worked if that was the case. They had the largest circulation in the world by the end of the week. Or maybe it was a satire to go after the people who still thought that there might be life on the Moon. There weren't very many of them, and they were too embarrassed to admit it when it became such a big deal. But this was kind of the last gasp for the idea of life on the Moon. So it's going to be harder. Where are we going to look? Well, we look at the planets in the solar system, and we can start with Mercury and Venus. They're right next to the sun. They're too hot. That's not going to work. Then there are these big giant planets. That's where most of the mass in the solar system is. But they're just giant balls of gas with no surface. Life as we know it just couldn't live there. We're left with a small zone that might be habitable over here. So we ask, what about Mars? It's the next planet beyond Earth. It's got the most similar climate to Earth, although it may not be that similar, as we'll discuss. It's a rocky planet with some atmosphere, and it's got the possibility, at least, of liquid water. So why do we care about liquid water? And you're going to hear more about liquid water next week. Well, every kind of life on Earth requires liquid water. Well, so maybe we're being Earth-centric if we're looking for liquid water, looking for life elsewhere. But if we think about what life might need to do, well, we have these molecules that need to get together, do chemical reactions, and it seems like it would need a liquid of some sort. Well, what liquid is there? The most common liquid in the solar system is liquid water, and it may be the most common liquid in the universe. So Mars becomes the focus. But to study Mars, we have to understand a little bit, and there went the microphone. Technology is not my thing. So to understand Mars, we have to understand a little bit about the orbit of Mars and Earth and how they interact. So every 2 years, roughly, Mars makes a close pass to Earth. It's called an opposition. And so here's Earth going around on its orbit, Mars on its orbit, and you can see there's a close pass, there's an opposition, and there are the dates up there. You can see that it's about every 2 years that this happens. So if you're an astronomer and you want to study Mars, the time to look is when Mars is close to Earth. It's at opposition. Similarly, if you want to send a spacecraft, you do it when Mars is close, when it's at opposition. So spacecraft gets sent every 2 years. But the other thing to notice is that while Earth's orbit is pretty close to circular, Mars has a very elliptical orbit. And so there are some close passes that are much closer than others. So when we're having close passes out here, as we are these days, they aren't very close, but in a few years they'll be close again. And you can tell that it's going to go on a cycle, and the cycle lasts about every 18 years. And so between looking every 2 years, but knowing that it's going to be great every 18 years, that's sort of defined the way Mars science has progressed. Now, from early observations, like by the 1800s, now this is an image from a modern 10-inch telescope, and that's probably a little, well, it's much better than any camera image you could take in the 1800s, probably better than most views astronomers had looking through their telescopes in the 1800s, but already you can see some sort of Earth-like features. It has polar caps. It has, well, some darker features, and it turns out it gets darker during the summer. Some argued, well, it's turning green, or maybe it's just kind of looks green because it's dark against a red planet and black sky, I don't know. But there were things that nobody knew. Things like, does Mars have an atmosphere? Well, you know it has an atmosphere because you see dust storms, but how much atmosphere? What's the temperature? You can assume that it's going to be colder than Earth because it's farther from the sun, but how cold is it? So these were unknowns, but people were looking. Now, each close opposition, telescopes were better than the time before, of course. In 1877, an Italian astronomer named Giovanni Schiaparelli observed what he called canali. Now, maybe that should have been translated as channels, but it got translated into English as canals. And this was something of a big deal, but it became an even bigger deal at the next close opposition, the next close pass. That's when this character comes into the scene. He's Percival Lowell. His father was Lowell, his mother was a Lawrence. There are colleges and towns named after Lowell and Lawrence all over New England. Percival himself was a graduate of Harvard, and he'd established a reputation as a travel writer. He'd gone to Japan when Japan was just opening up to the West and wrote a best-selling book about it. He took a telescope along, by the way. And as the next close opposition was coming up in 1895, he learned that Schiaparelli's eyesight was failing him. And in the 1800s, as an astronomer, your eyesight was pretty much what you had. And Lowell decided that he needed to do something about it. Well, what can you do about it? If you're rich, which Lowell was, you might think of paying to build a great telescope for the professionals. Now, if we have anybody in here who can fix a microphone, if we have anybody in here who would like to write, say, a $20 million check for the giant Magellan telescope you'll be hearing about next week, I'm sure Dan Petricelli would be glad to talk to you after the lecture. But if you don't have that kind of money, you might consider doing what I and the other speakers have done, which is go to school, get an advanced degree, and become a professional. But Lowell, well, he had the money, but also remember, he was a graduate of Harvard. Well, it was math, not astronomy, but isn't that close enough? So he decided that he would build himself the world's best telescope. And he was serious about it being the best. He knew, for one thing, what astronomers were beginning to figure out, which was that how well you can see through a telescope doesn't depend just on there not being clouds, but sometimes, you know how the stars twinkle? Well, that's because the atmosphere is moving. And if you're an astronomer in the 1800s, you wait for those moments when the atmosphere on your line of sight just stops moving for a second, and then you memorize what you're seeing and you sketch it down. Of course, you'd rather have more of those good moments, and that might mean getting where there's less atmosphere above you, higher altitudes. It might mean getting where there's less water above you, a drier place. Lowell, remember, is well-traveled, so he decided that the best place to put the best telescope in the world would be Arizona Territory. So he hired a young astronomer who had just graduated from Harvard, a gentleman named Andrew Ellicott Douglas, to go around Arizona looking for the best site to put the world's best telescope. He started in Tombstone about a dozen years after the shootout at the OK Corral, and we're going to put the world's best piece of high-tech equipment in Tombstone. Well, for whatever reason, he didn't think Tombstone panned out. He came up to Tucson. It was January. It rained. Who would put a telescope in a rainy place like Tucson? Next, he went to Tempe. And I guess in 1895, maybe the reasons for not wanting to be in Tempe are as clear as they are now. He said it, decided that wouldn't work. Time goes on. He goes on to Flagstaff. By now it's spring. Spring in Flagstaff can be drop-dead gorgeous, and it was that year. And he wired Lowell, this is the place. And so Lowell set up his observatory in Flagstaff, shipped the parts up from Tucson, where he'd originally shipped them, thinking it would be someplace in southern Arizona where they'd put his observatory, and built Lowell Observatory, which is there today doing great science. Now, every night, Lowell, who's sitting at the telescope there, or Douglas, or another astronomer, would look all night at Mars and see what they could see. And what they saw was canals. Not canale, but canals, straight lines connected to one another, intersecting at junctions. Well, what does that mean? And Lowell had an interpretation for that. He said that the canals are carrying water from the polar caps, that they originated at the polar caps, they moved down to the equatorial regions where plants are growing. And for good reasons, although they turned out to be wrong, he believed that Mars had once been much warmer and was cooling off, drying out, so there could have been enough time for such an advanced civilization to develop to be able to build canals. So wait a minute. If there are canals, there have to be canal builders. That means there's intelligent life on Mars. Okay, well, scientific opinion was mixed. At first, if somebody said, I can't see canals, Lowell could rightfully say, that's because your telescope isn't as good, or your sight isn't as good, and he'd be right. But over the years, more good telescopes got built at comparable sites or better. And by about 1910, the idea was dead in the scientific community pretty much. Douglas, by the way, had a falling out with Lowell, in part over whether he could see the canals or not. And he also had second thoughts, decided he'd made the wrong choice the first time, so he came to Tucson and founded the astronomy department here. The tree ring lab later, but that's a whole other story. Meanwhile, Lowell was studying Mars as much as he could. So, for example, he wanted to know how much water is there in the atmosphere of Mars. Of course, the problem is you've got to look through the water of the Earth's atmosphere to see Mars's atmosphere. But he remembered that there's this thing called the Doppler effect, where the frequency of light or sound will change if something's moving toward you or away from you. And so he looked when Mars was moving toward or away from the Earth, used spectroscopy, where you break up the light with something like a prism, and looked for the gaps where water would absorb the light, and tried to find water in the Martian atmosphere that way. It didn't work. His instruments weren't good enough. There wasn't enough water there. But keep that in mind. That idea will come back. Okay, so scientific opinion was mixed. The idea died pretty quickly. Public opinion, on the other hand, Lowell was eloquent. He could pack houses in Boston and around the East Coast telling his story of life on Mars, and the public loved it. It's a great story. But, people read into it what they wanted to. That's kind of what he was doing in the first place. Let me just give you a couple of quotes. One is from the editor of a newspaper in Boston. This is 10 or 20 years before the Russian Revolution, and he believed that to build canals like this, the people of all nations must cease regarding boundary lines and have become one class as well. He said that Mars is carrying through our heavens the heart-red flag of socialism. As you might imagine, Lowell, as a rich Bostonian, did not quite see things that way. He said that only the very ablest could be in charge, and from top to bottom, each individual has his place and fills it. Everybody saw what they wanted to see. And that's one of the beauties of this idea, is that it's just such a compelling story. And it wasn't just editorialists. This idea of a civilization dying of thirst became the theme for a half-century of great science fiction. It started with the very first alien invasion novel, War of the Worlds by H.G. Wells. Orson Welles made the greatest radio play ever out of that about 40 years later. Edgar Rice Burroughs, starting about 100 years ago, put together this series of books about the adventures of John Carter on Mars, wildly popular then, still popular today. There was a movie about John Carter on Mars 3 years ago. And finally, in about 1950, Ray Bradbury wrote what might be the best one, the very lyrical Martian Chronicles about the Earth invading Mars with the astronauts, that sort of thing. Bradbury, incidentally, had this Mars that's this desert that kind of sounds and looks like the Arizona desert, which might be because when he was a teenager, he lived in Tucson. But after the 1950s, Mars science fiction no longer has this civilization dying of thirst. It's about exploration. It's still popular. There will probably be another TV show, for instance, with a plot based on Mars in about an hour and 40 minutes. I just saw the previews. Castle on ABC. Anyway, why did that change? And the answer is because we've been there. We sent spacecraft and we could see. There are no canals. It's a cold place. The low temperatures in the winter are dry ice temperatures. Up in the summer, at the hottest part of the day, in the warmest place on the planet, in the middle of summer, the temperature might be as warm as it is outside here today. But the low will be 100 degrees colder that night. It's a desert, okay? And it's a cold desert at that. But it's still more Earth-like than any place else in the solar system. As we've learned more about it, we've learned that there are pieces of evidence that there's been liquid water in the past, that there is water ice today on Mars, but is there life? The first time that NASA sent a mission to look for life, actually it's the only time that there's been a NASA mission with the express purpose of looking for life, was the Viking mission in 1976 to Mars. How do you look for life? Well, one of the things they did was they included a camera. They looked to see if anything moved, and no, nothing moved. They included something called a gas chromatograph mass spectrometer to see what kind of organic materials was there. Because they knew there were organics. There are meteorites falling on Mars, just as there were the meteorites falling on Earth that may have contributed to life on Earth. So they knew there would be some organics. What did the conditions on Mars do to those? So they measured, except they didn't find any. It wasn't that they didn't find very much. They couldn't measure any with the abilities that spacecraft had. That sounds bad for life. But they had several other experiments. They went ahead and ran them. They were all basically experiments looking for metabolism. They'd scoop up some soil and they'd pour some water on it, or shine a light on it, or they would give it food, a broth, basically, made of simple organic molecules. And they said, they agreed beforehand, if it's A, we found life. If it's B, we haven't found life. And so, of course, they got result C. What happened was that they got lots of chemical activity going on at the start, but not the sorts of things expected out of life. So what do you do with that? And there's no organics. It was controversial. It turns out that of the people studying it, hello, there we go, with one exception, no one involved thought that they had found life on Mars. So what's the take-home from that? Well, from Viking, the idea was there's no life on the surface at Viking. These weird results, they finally decided, oh, you know what could do that? Mars doesn't have an ozone layer, so there's ultraviolet light coming in and flooding the surface. That can cause chemical reactions in the soil, and you could get things like peroxides, like hydrogen peroxide. You know, you pour it on a wound and it sterilizes things. It chews up organic molecules, and it bubbles away, lots of chemical action. And that could be what's going on, that the surface is not just sterile, it's sterilizing. Great idea. They couldn't quite make it all fit, and it turns out it wasn't quite right. But hold on to that thought for a little later. That mystery got solved 2 months ago. But there are other questions. So, for example, what about life in the past? What about life under the surface? People like Imre Friedman, who was an astrobiologist, got to thinking about, could there be life in conditions that we aren't used to finding life? And so he looked in places like Antarctica, in places like the Negev Desert in Israel. There were others who were looking deep under the ocean, trying to say, well, what does life really require? For example, the assumption had always been that all life on Earth starts with photosynthesis, sunlight, right? The answer turns out to be wrong. All life requires an energy source, but that energy source might be sunlight, it might be chemical reactions, it might be geothermal vents. Radioactive decay within rocks is even the energy source for some microbes on Earth. So life lives in places that we hadn't thought about. And sometimes these are places with extreme conditions. The record, I think, is something that lives best at a temperature 2 degrees below the boiling point of the water it lives in. There are things that live in extremely acidic conditions or under high salt contents. This picture over here is of a hydrothermal vent in the Southern Ocean off Antarctica, 1.5 miles deep, no sunlight anywhere near, and all of those little white things, those are all crabs. This is a burgeoning ecosystem. Okay, so life can survive places that we hadn't thought about. Okay, and as we looked at Mars, we found there is evidence that there's sometime been water there. So for example, there are these giant outflow channels that look like they might have been cut by gigantic floods. U of A's Vic Baker is one of the experts on that. There are valley networks that have this sort of branched appearance, like the washes have around here, except they have impact craters on them, so they're very old, but they look like they were rained on. There are craters that we find that, a good crater on the moon, it'll make a hole and it'll throw rocks around. But some of the craters on Mars, it looks like things have just kind of flowed out from the crater. What can cause that? Well, maybe water ice. And moving from the kilometer scale to the millimeter scale, here's a meteorite called Lafayette. Meteorites are named after the place where they're found. This one actually should be called West Lafayette because it was found in a drawer at Purdue University. But this meteorite, the image you're looking at, they cut it very thin so that you can shine a light through the rock. And the whitish stuff, that's all the normal minerals that you find in rocks. But the rusty colored stuff, it's not exactly rust, but it is oxidized iron in minerals that require liquid water to form. Now, there were some arguments. The people studying these thought that these came from Mars, that the minerals formed on Mars, but of course, the meteorite's been on Earth for a while. There's water in Indiana. That could be where it formed. So a gentleman named Alan Treman went in with a needle and some tweezers and plucked out some of the bigger ones of these, some that were almost 1/10 of a milligram in size, and sent them to my lab, and we analyzed them and found out that they're a few 100 million years old. Well, I don't know how long it was in the drawer at Purdue, but it wasn't a few 100 million years old. That has to be Martian, okay? In this sort of setting, okay, we know there's been water, at least in the past, comes a fantastic claim in the mid-90s by Dave McKay and some colleagues at NASA's Johnson Space Center in Houston. They said that this meteorite, Ellen Hills 84001, it comes from Antarctica, but that this is a meteorite from Mars that contains evidence of past life on Mars. And their arguments were that the meteorite's from Mars, it contains a mineral, carbonates, that are from Mars, that these carbonates, as well as some other minerals, had to have formed as a result of the actions of microbes on Mars, that there's organic material near these carbonates. I mean, there should be if they were formed by living things, and that there are microscopic fossils. So Guy Calsamagno talked a little bit about this meteorite. Let me talk a little bit more, and I may give you a slightly different viewpoint on it. So start with, is it from Mars? There's a group of meteorites called the SNC meteorites that are agreed to be from Mars because they have the fingerprint of the Martian atmosphere. What do I mean by that? Well, this thing is a patch of material that was melted by an impact when the rock got hit by something, and it got melted and then cooled so quickly that it couldn't form good minerals, so it became kind of glassy. If you melt that in the lab and measure the gases that come off, they match the gases that Viking measured in the Martian atmosphere. They don't match any other planet. They don't match any other meteorites, but they match Viking. There are some other chemical hints as well, but most scientists would agree that these come from Mars. Okay, well, what about the Ellen Hills meteorite? It's not quite chemically the same as these, but we looked at a chunk of Ellen Hills and, in fact, found that when we melted a chunk of Ellen Hills, though it didn't have the glassy patches, it had the same fingerprint of the Martian atmosphere. And there are other chemical clues as well. So most scientists agree that this meteorite's from Mars. Okay, so check one for McKay. The carbonates, well, they are these orangish things, and they don't look like the carbonates that living things form on Earth, but conditions are different on Mars. One group found how old the carbonates are. They're 3.9 billion. They're from Mars. another group was working, trying to figure out what the conditions would have to be. And they found that, yeah, it's low temperature, liquid water conditions, but they were able to make them in the lab and then go out and find places where they saw carbonates like that weren't formed by living things. Oh, not so good. How about this other mineral? It's called magnetite. Some of you may have chunks of magnetite in your front yard. It's a big, dense black rock, magnetic. They make magnets out of it. But these are actually magnets as well, or can be. There are microbes that make tiny magnetite grains to steer by using the Earth's magnetic field. These ones in the Allen Hills meteorite are about 10 nanometers across. A nanometer is 1/1000th of a meter. These are tiny, but they're the size that terrestrial microbes make. Unfortunately, the same group that figured out you could make the carbonates without life around figured out that you could make magnetites like this as well, and could find where you could get some in Iceland, it turns out. And so at this point, two of the key pieces of Dave McKay's story that was going to be one of the great finds of the century have gotten some holes shot in them. And you might wonder who the lab was that tested this so well that they found other ways to do it. Well, it was a lab at NASA's Johnson Space Center in Houston, where Dave McKay worked. And the leader of the lab was a gentleman named Gordon McKay, Dave McKay's younger brother. I have no idea what Thanksgiving was like. Okay, organics. You should have some organics around. They're organics, but they're not amino acids or DNA or proteins. They're the stuff that life runs on. They are these polycyclic aromatic hydrocarbons, the kinds of things that you get when you burn a steak. And worse, Tim Joll at the U of A showed that much of the organic material in Allen Hills is terrestrial contamination. And when another group studied these with a different technique, they said, well, yeah, there's some near the carbonates, but they're no more common there than anywhere else. So this one doesn't look so great either. Finally, the really photogenic Martian fossils, this worm-shaped thing, that was very popular. X-Files, if you remember the TV show, they had a two-part episode based on this meteorite, and they had the worms crawling out of people's eyes, all that sort of thing. You could buy plush toys shaped like this, except, well, the plush toys were much too big. Actually, the worms crawling out of people's eyes were too big because these are really 100 nanometers long. That is less than a millionth of a meter long. They're tiny. And in fact, they are smaller than any known living cell on Earth. And you remember those magnetite grains? If this guy made the magnetite grain would be sticking out the sides. This guy is so small. This led to a series of conferences. What's the smallest a living thing could be? If you break open a rock on Earth, you see things like that, and there was a guy who said, yeah, they're nanobacteria. So people started studying those. Can you culture them in the lab? Is there organic material associated with them? And the answers turned out to be no. So this one didn't do very well either. So the Allen Hills, life in the Allen Hills meteorite idea is pretty much dead, but I think it's an interesting episode in science, and it was a lot of good science happened. One of the things I found interesting was to see how scientists thought about it. So at the first major conference where these results were being presented and people had started studying some of the other possibilities, I took a survey. I asked two simple questions. The first was, what are the chances that there is or ever has been life on Mars? I didn't ask, has there been? I said, what are the chances? This is scientists, okay? I got over 120 responses. Nobody said 0. Nobody said 100%. But the average answer fascinated me. 50%. We don't know. The other question I asked was, what are the chances that this rock, the features in this rock were caused by life? And the answer to that was 20%. How do you take that? Well, the average scientist there, and this was only a few months after this had been announced, said only 1 in 5 chance that these guys have got it right. But boy, a 1 in 5 chance that we're looking at life from Mars, that's worth going after. And people did go after it. 5 years later, I tried taking the survey again. Nobody was interested. Okay, so let's move on from that. And people did move on. There are more spacecraft in orbit. They find gullies that seem to have formed recently. Well, how recent? Maybe yesterday, maybe a million years ago. There are no craters on them, though. The Opportunity rover found rocks that looked like sedimentary rocks formed on Earth under slow-moving liquid water. LPL, my organization, Bill Boynton, built an instrument called a gamma-ray spectrometer suite that included a neutron spectrometer that could look at the surface of Mars and see what kinds of neutrons and how many, or what energies and how many of them were coming off, which is a measure of hydrogen, and found that there's a lot of hydrogen near the surface of Mars. In fact, their calculations said there should be places where in the top meter of the surface, half of the volume is water, ice. In part because of that, NASA funded a mission to go to the polar regions of Mars, headed by Peter Smith of U of A's LPL, and they found evidence for water ice. And it comes from, some of the best evidence is from this picture. Now, they took a scoop, and you see some stuff, and a sol, by the way, is a Martian day. It's about the same as a terrestrial day. They took another picture 4 days later, and things had changed. In particular, there were a bunch of things that went away. What would go away? Well, dry ice would have gone away before they took the first picture. Salt would never go away. Liquid water. Or not liquid water, but water ice. Highrise. It's an instrument taking the highest resolution pictures of the surface of Mars that have ever been taken from orbit. They're downloaded about 1/4 mile from here. Alfred McEwen is in charge of that one. They can find fresh craters on Mars. This one is about 6 meters, 20 feet across. And they probably found it weeks or days after it formed in October. And then they looked again the next time they went over that area. The ice was gone. And there's a bunch of craters like that. And they also found things that they call recurring slope lineae. Now, what you'll see here is that down here, there are these streaks that form and stretch, and then fade away. Okay, it comes back around, and you see them forming, extending, and then going away. And when this part warms up, they form there. And they've seen this, and they form seasonally in the springtime, all over Mars. They've seen this at a whole bunch of different places. What's causing it? Well, don't know for sure, but the most likely thing is that you've got water, liquid water, moistening the soil, and then it dries up again. And it's a seasonal thing. So we've got all sorts of evidence. Now, I want to come back to one other thing that makes life look a little more likely on Mars, and that's that, you remember that lack of organic material that Viking had? Well, the Phoenix Mars lander also included a little wet chemistry lab. Now, when I say little, I mean, little wet chemistry lab. It's a spacecraft, but they analyzed the stuff they scooped up, and they found something called perchlorates. Chlorine and oxygen, then combined with calcium or something like that. But one of the fascinating things about perchlorates is that if you heat up perchlorates and organic molecules together, they'll react all over the place, and the organics will disappear. They found perchlorates in the soil of Mars that blows everywhere. How did Viking test for organics? They heated up some soil to see what came off. So maybe it wasn't that the soil was sterilizing, but the experiment was. How do you test that? Well, we've got another rover there that's a little more capable called Curiosity, and they verified, yep, there are perchlorates there. Yep, we heat up the soil, we don't get any organics off. We find other ways to release that should release organics without heating it up and getting the perchlorates involved, and as of last December, we find organics on Mars. So after 40 years, yes, there are organics on Mars. We just didn't understand it all. The other interesting thing about perchlorates, it lowers the melting point of ice. So there could be brines more likely to form. Could life live in perchlorate-rich water? I don't know, lives everywhere else. Another thing I want to mention is methane. Methane is the simplest combination of carbon and hydrogen, and there are these microbes, bugs, that are methanogens. As the waste product of their metabolism, they give off methane the way we give off carbon dioxide when we breathe, the way plants give off oxygen when they photosynthesize, except methanogens give off methane. We find them often in extreme environments. We also find them in the stomachs of cows. You can figure out where that's going. But the evidence of methanogens appears very early in the fossil record. And some people have suggested that if we find an atmosphere that has methane and stuff like water and carbon dioxide and oxygen, those should react together. They shouldn't all be there at the same time. And so if there's methane and oxygen-rich stuff, that may be a biosignature, a signature that there's life there. That's why we have methane and oxygen and water in our atmosphere. What about someplace else? Well, Mars is basically oxygen-rich. You wouldn't expect to see methane. Calculations say that if you put methane in the atmosphere, it would go away in about 300 years. Except, starting in 2004, 3 different groups reported finding methane in Mars' atmosphere. Not a lot, 10 parts per billion, but enough that it shouldn't be there. One group was using a European spacecraft. 2 other groups were using telescopes. Now, how can you find methane in the Martian atmosphere from a telescope on the surface of Earth? Because you have to look through all the methane from the cow farts in Earth's atmosphere to see it. Well, they looked when Mars was moving toward the Earth or away from the Earth, the way Percival Lowell looked for water. Except their instruments are more sensitive. And they said, yeah, we see the signature of methane. And 90% of the methane on Earth comes from biological sources, but not all of it. So there are other things that could cause it. But boy, that biology part, that's really interesting. So of course, Curiosity, when it got there, one of the first things they did was to measure methane. And they saw no methane. Great story, but didn't work. But if you're part of the Curiosity team, and you've got this instrument that can measure methane, and you've got this rover that is driving endlessly toward this mountain where they want to do other stuff, but is doing nothing in the meantime, well, heck, might as well measure methane while you're going. And so they just kept measuring methane. And this plot, remember, a sol is basically an Earth day, so they measured methane, and no methane. Incidentally, the lines, the length of them, is the uncertainty on the measurement. That's basically, there's no methane. No methane. Well, wait a minute, that's interesting. And, I don't know, that's higher than those. So then they're doing other things on the surface, working with rocks, all that sort of stuff. Then, a year and a half in, they start measuring methane fairly regularly, and there is 5 to 10 parts per billion, by volume, of methane. That's what everybody else was seeing. There is methane on Mars. So then they have a way that they can measure it more precisely, shrink those error bars, but it uses up spacecraft resources that are kind of one-time-ish. So they don't want to do it very, very often, but they decided this is worth finding out how much there really is. We'll do a really precise measurement. And so they did. There's almost no methane. There's a little bit, but almost none. Ooh, let's try that again. About the same amount. Well, wait, maybe when we change measuring techniques, we're doing something wrong. Let's try it the way we were measuring it before. Still no methane. Where does this go? I don't know. I really don't. Because for one thing, the methane shouldn't be there. For another, if it was there, it shouldn't go away in a month because it just doesn't react that fast. Maybe their measurements are wrong. The Curiosity team has studied which direction the rover was pointed, how much it was driving, what gears had been turning, all that sort of stuff, and can't find anything, but maybe they're wrong. Don't know. So just stay tuned. Okay. Final thought about life on Mars, and then we'll go on to a couple of other interesting places. This is panspermia, the idea that life can move from one planet to another. Remember, we have rocks from Mars. Now, they took millions of years to get here, but if you have an impact on Mars and it launches a rock with just the right velocity at just the right angle, it could get to Earth in a matter of months. And people have studied some of these extremophiles and have found that there are things that could survive in space for the length of time that it would take to get from Mars to Earth. So if there's some deadly plague on the surface of Mars, it's been here. Okay? It's also true that we've contaminated Mars already. I guarantee we contaminated Mars about 6 months to a year after the dinosaurs went extinct. That was an impact that should have thrown off rocks, some of which should have gone to Mars, with terrestrial microbes. But it's more interesting to think, well, we've seen all this evidence that Mars was probably wetter in the past. What if it was a more clement climate? Maybe life went from Earth early Earth to Mars. Or wait a minute, maybe if life formed first on Mars, it moved from Mars to Earth. And who knows? We could be Martians. Okay, but we've sort of exhausted the one planet that we could have life very much like life living on the surface of Earth. But what about any other places? And it turns out that as we learn more about extremophiles, we realize there are other places where life, terrestrial life, could live if it got the chance. One of these is Europa. Europa is a moon of Jupiter. It has a very cold surface. That doesn't sound conducive to life. No atmosphere. But the surface is also very smooth. You see one impact crater. Most moons, you see impact craters all over the place. It has no mountains to speak of. The tallest feature is something like 1 kilometer high over the whole entire moon, like the surface is soft. And it's been suggested on theoretical grounds by people like Guy Consolmagno that you could have an ocean of water underneath a crust of ice. Incidentally, if that picture looks familiar, that may be because you've been at this series. That's part of the logo. Okay, so what about Europa? How could we get that crust, or that ocean rather, under the crust? Well, the way you can heat a moon, you really have to have a couple of things, at least as far as Europa is concerned. One of them is something called orbital resonances, and the other is tides. And I'll demonstrate what I mean by this. So Europa is between the moons Io and Ganymede. So Europa is the one in the middle. And note that every time Io and Europa make a close pass, it's right over here. There was one over here. Next time they come around, it's right over here, same spot, because Europa goes around exactly half as fast as Io. It's an orbital resonance. And Europa goes around exactly twice as fast, boop, as Ganymede. So every time Europa is close to Io, it's right there. Every time it's close to Ganymede, it's right here. Its orbit is constantly getting tugged, and meanwhile, here's big old Jupiter in the middle, trying to stretch it, and you get these tidal forces that basically try to rip Europa apart. And it stretches and tugs and heats the planet up. In the case of Io, which is even closer, that leads to the most volcanically active moon in the solar system. Okay, but so we've got Europa, but what would conditions be like? Well, so we have this idea, but is there any evidence? There was a spacecraft called Galileo that was in orbit around Jupiter for 8 years. One of the things it had was an instrument to measure the magnetic field of Jupiter. Jupiter has a huge magnetic field. But when it would pass by Europa, the magnetic field would dip and change as though you'd just gone by, a whole bunch of salty water. That sounds interesting. Galileo also took high-resolution images of the surface, and you get this sort of jigsaw puzzle-looking surface. And in fact, Rick Greenberg at LPL and his group literally took images like this and cut them up into effectively puzzle pieces and tried to see if they could put them together. And they could, suggesting that you had a surface, that it somehow broke apart, floated around on water, and then refroze. And more recently, in 2012, there was a measurement with the Hubble Space Telescope of water vapor at Europa, suggesting that maybe there's a plume venting water from Europa. Okay, so what would the conditions be like? Life would be tough. In the ocean, there's no sunlight. You're under, well, people disagree whether it's a few kilometers or 10 or 20 kilometers of ice. It'd be high pressures. Of course, there would be liquid water, by definition, and there might be things like geothermal vents. So is there anything that we could imagine that could live in a place like that? That's the conditions. Okay? So maybe there could be life in Europa. But how are you going to find it? I mean, maybe you can drill through miles of ice, but not this decade or next or the one after that. So does the surface somehow interact with that ocean so that we could measure something coming up from the ocean? Well, the surface has these ridges that crisscross the entire planet. And Rick Greenberg and his group suggested that maybe what's going on is that when the tides stretch it, the crust stretches apart, some water comes up, it stretches back together, stretches apart, water comes up, pushes back together, and you build up a ridge. Actually, every ridge is a double ridge. Okay, so there may be interaction with the ocean there, and there's that plume. Maybe you can see stuff in that plume. NASA has recently decided that they are going to try to send a mission to Europa, launching in 2022. They've put out a call for instruments on the Europa mission. Don't know whether we'll get any of them, but we have several proposals in, so stay tuned for that one. But is Europa the only place like this? And the answer turns out to be no. There is a moon of Saturn called Enceladus. It's a small moon, but it's in an orbital resonance with Saturn's largest moon, Titan, which we'll talk about in a few minutes. And in a way, it kind of looks like Europa in this part, very smooth surface. Well, this part has lots of craters, but down in the southern part, it's very smooth, except for these sort of tiger stripey looking things. And so people said, well, maybe it has had some sort of ocean or something too. And there's a spacecraft that's in orbit around Saturn now called Cassini that found that Enceladus is venting water from those tiger stripes. So here's just a picture with the sun on one side of Enceladus and the spacecraft on the other, but they also flew through those plumes and they could measure, yes, it's liquid water. So Enceladus has liquid water. Okay, but it's also hard to get to. How about something closer? The biggest asteroid, it's also classified as a dwarf planet like Pluto. The biggest asteroid is one called Ceres. It's 1,000 kilometers across, nearly as big as Pluto. And recently, the last few years, people have observed that there seems to be water vapor coming from Ceres. Now, I don't know how it would get a subsurface ocean, but I know people are talking about it. Now, if you want to know what the best image we have of Ceres is, that's it. That was taken a week and a half ago, because the first spacecraft to visit Ceres will go into orbit next month. So Ceres, stay tuned. And if it's venting water, that's an easier place to get to than Europa or Enceladus. We'll see how that plays out. Okay, so we've talked about life as we can imagine it, but how about life as we don't know it but can vaguely imagine it? Not a place where life from Earth could live, but life unlike Earth. And that might be Titan. Titan is Saturn's largest moon. It was discovered by our old friend Christian Huygens, if you remember from the start of the lecture. And the Voyager spacecraft in the 1980s did this grand tour of the outer solar system. One of them went past Jupiter, Saturn, Uranus, Neptune, all the way out. The other one went past Jupiter, Saturn, and then took a detour. Why did it do that? It's because they wanted to study Titan and get up close to it. Why? Because Titan has an atmosphere. That, incidentally, was discovered by Gerard Kuiper, who later founded the Lunar and Planetary Lab, so I'm indebted to him. But people have figured out it's got this atmosphere, and conditions are right that it could have clouds and rain and rivers and lakes. There's a problem, though. Those clouds and rains and rivers and lakes would be liquid hydrocarbons, not water. They'd be things like ethane or methane or propane. So they targeted one of the Voyager spacecraft to get an up-close look. And as they approached, it looked like a big fuzzy orange ball. And as they got closer, it looked like a bigger fuzzy orange ball. And as they got really close, it looked like a really big fuzzy orange ball. And they went headed off to nowhere. So the Cassini mission, which was launched in the 90s, is still in orbit. But when they got to Saturn in the early 2000s, they carried with them a probe to go into the atmosphere of Titan. And the probe was called the Huygens probe. The camera on the Huygens probe was built at LPL, at U of A, of course, by Marty Tomasco and his group. Oh, incidentally, you can see Enceladus in the background here, but we're approaching Titan and heading in. Now, that orange fuzz, that's basically a layer of smog, really. It's the same compounds. And we've got to get through that, and then we'll see what the surface looks like. Does it look just all like craters? And no, it's not this cratered lunar-looking surface. You've got these branch networks that look like rainfall, but it looks more like dry washes than active rivers. We don't see anything running in them. And incidentally, I should mention that the Huygens probe was actually spinning the whole time, so they had to kind of de-spin it to get this movie put together. Now, they didn't see oceans and clouds, but Cassini has instruments that can see through that haze layer, and Cassini has seen big lakes and has seen places with clouds and has seen places where all of a sudden the surface changes as though a whole bunch of liquid's been dumped on it. So it is kind of that place that people had predicted. Now we're coming into the surface, and incredibly, the Huygens probe actually made a soft landing on the surface of Titan, the only spacecraft that's ever landed on the surface of a moon of a planet other than our moon. Okay? So this is the only one. Okay, so what are conditions like at the surface of Titan? Well, for one thing, it's cold. It's triple digits below zero cold, and I don't care whether it's Celsius or Fahrenheit, triple digits is cold. Okay? The rocks are water ice, really, but that's a rock there because it's so far below zero. It gets about 1% as much sunlight as Earth does, so it's not the place you want to go for your vacation. And no life on Earth could survive. It's too cold, there's no liquid water. But we said at the start that water seems to be the magic liquid, but we think that life should require some liquid. There is liquid. Could life of some sort live there? Biologists are starting to talk about what kind of life might you be able to form. And even if not, some of the reactions going on in the atmosphere might be the sorts of things that were happening on the early Earth before there was life. So we'll be back to Titan, though not for a decade or two. So where does that leave us? Is there life in the solar system? Well, on Mars, unfortunately, there's not the civilization that Lowell or the science fiction writers imagined, but there may be burps of methane. What do those mean? I don't know. Maybe there was life in the past, despite the fact that most scientists don't like the claims about Ellen Hill's 84001. Well, not that they don't like them, they just think they're wrong. The possibility of life in the past is really still there. These subsurface oceans, fascinating, fascinating concepts. There are kinds of life on Earth that could survive if you transplanted them there. But did life start there? And can we find a way to test it? Titan? Well, maybe, but it would not be like life on Earth. That might be the most interesting of the bunch, but it'll be a while before we can get there. So what's the bottom line? I'd say it might be the 3 favorite words of a scientist. We don't know. Coupled with, we know some really good places to look. Thank you.